Questions? Yeah. 10. You got it. 10. All right, number 10, we have e to the 4 minus x times 2, e to the 2x plus 1 raised to the third. Okay, so you want to take care of this one first. So that's going to come here, and that's going to distribute to those. Okay, so that's going to give me e to the 4 minus x. 2 times 2 times 2 is 8. And then e to the 6x plus 3. Do you feel comfortable with the math I just did? Okay. Now I have a multiplying, so my like bases, the exponents will add, so 8 just comes across, e, and then I'm going to go 4 plus 3, which is 7. Negative x plus 6x is plus 5x. That answer is technically fine, but they kind of want to have the variable come first. So if you gave me either one of those answers, I think it's appropriate. If it was multiple choice, the bottom answer would be the one that would be given. Is that all right? Anything else? Yeah. 2-7. F at x is equal to e, or negative e, to the x minus 2 plus 4. Okay, so there's a couple things that you have to realize. If I had e raised to the 0 power, that would be 1. E to the 0 is 1. Does that make sense? Okay, let me increase this graph a little bit. That should be good. So let's deal with my asymptote first. So I get that. And then from there, I said I want to try and get e to the 0. So that means if I plug 2 in, I'd get 2 minus 2, which is 0. E to the 0 is 1. There's a negative out front, so that would give me negative 1 plus 4. Negative 1 plus 4 would be 3. So I get 2, comma 3. And that's fantastic. And then something you have to just kind of have in your wheelhouse of things to remember is e to the first is roughly 2.7 rounded to 1 decimal place. Okay, it has to be like a go-to to know. Okay, so what would I have to plug in for x to make it to the first? What would I have to plug into x to make it e to the first? 3. So I'm going to plug 3 in. If I plug 3 in, I get e to the first. E to the first is 2.7. There's a negative, so I get negative 2.7 plus 4. If I combine those together, that comes out to 1.3, I believe. Does my math look about right? So 3 comma 1.3. So 3 comma 1.3 is about here. So this is what it's going to look like. So again, the main thing that you want to remember is e to the first is roughly 2.7. Yes, it's an irrational number that goes on and on and on forever, but if you kind of keep that in your wheelhouse, you're good to go. Anything else you want to take a look at? Good. Perfect. All right, I didn't give you notes yet, or did I give you notes yet? No, okay. All right, so before I give you your notes, I'm going to add one more question. I just wanted us to kind of think about this. Let's say I had okay, so I want you to kind of think about this. How can we make our exponential function correct? I want to come up with the equation that goes with that. Okay, so I'm going to put a few things up. There you got it. that are kind of a go-to. There you go. There you go. There you go. Uh-huh. Yep. I made more of an obstacle course for myself than it used to be. Did everyone get one? Or did I forget anybody? Got y'all? Cool. Okay. So this is not on the notes. You could put this on the very back page if you wanted to. Obviously, this is, I think, 2 days worth of notes. So I got 9D and E. Yeah, so this will be, and then F. The F will go with, I haven't decided if F is going to be Monday's lecture or if it's going to be a review on Monday, because a week from today we will do a quiz on 9A through E. Okay? But I've heard, maybe you all have heard this as well. Monday, we're not doing remote where I'm teaching, but I probably will put a review video. Would that make sense? And I might put it in play pause it so I can verify who watched it. Meaning you just click on the thing on Schoology and then I can tell who watched it. Maybe points for watching it. Okay, so let's think about this problem. How are we going to approach this problem? Let's say I got y equals a times b raised to the x plus c. Can anyone guarantee me what c is right now? You think? -3. Very good. So far, because of the asymptote, I know this. Anybody have trouble with that? Okay. So now, one way we want to look at this is we want to look at our point. Our first point that we want to look at is what is closest to the asymptote. You want to find something that is 1 away from the asymptote, which is this. Agree? Okay, so that's going to mean something. And then I'm going to think about my second point where it's that. So this is a distance of 1, and this is a distance of 2. Agreed? With that known, let's see if we can make this work. I know I got that -3. I think my b value, I can go with x plus 1. Is that okay? And do you see why I would do an x plus 1 versus just an x? The x plus 1 is taking place because normally this point right here would be where it's crossing the y-axis. But it shifted left 1. So remember when things are grouped, and if it's an exponent, that's technically still grouped. Technically, this is in parentheses. We get lazy when we drop the parentheses. But that means that the shift of 1 has taken place. Being that we don't have that far of a gap right there, we're going to go 1 times. But let's think about this. Bx plus 1 minus 3. Okay, how can we solve that b value? Well, right now I have 3 variables up there. I have y, b, and x. Agree? So let's figure out what our b value is. And the reason I can figure out my b value is I can do one of 2 things. I can plug in the point -1 comma -2, or I can plug in the point 0, -1. So I have a choice. I could pick this point, or I could pick this point. Now, one of the points will be a little bit easier to use. A lot of times a point, if it involves the point 0 as either the x or the y, that becomes a little bit easier to use. Agree? So I'm going to choose to use this point here. Okay, so that's an x value, that's a y value. So I'm going to get negative 1 equals 1 times b, which we don't know. And then I get 0 plus 1 minus 3. So I get negative 1. I could drop that 1. B to the first is the same thing as b. Agree? So add 3 to both sides. So I'm going to get b to the first, or b, is equal to 2. Oh, now I have my whole equation. So now I have y equals 1. You technically don't need that 1, but it's okay if you put it. 2 raised to the x plus 1 minus 3. That's my equation. So you have to use sometimes a little bit of logic on it. And you have to realize there are some things that will make the graph flip upside down. Okay? So if this graph was flipped downward, so if this graph looked like this, if that graph did something like that, that's going to give me a negative out front. It's still not the right graph anymore, but that's one thing that you have to kind of look at. Like the negative automatically comes out front, it starts looking like that. If the graph looks like something like this, that becomes a decay. So this here, that means my b has to have a negative exponent. Okay, so just some things to kind of just keep in your wheelhouse to think about. Okay, but let's go back to the lesson now. So we'll go with the notes. So I just want to, and we'll warm up on something like that again on next time we have class. But I just wanted us to think about that, kind of how we would maybe develop those graphs. Okay, we're going to talk about more exponential growth and decay. We're going to deal with some of the exponential growth and decay that deal with e, which is the exponential. Okay, remember e is basically 1 plus 1 over n raised to the n power. That's how we generate e, is when our n value goes to infinity, and we basically sum it up. It's a summation. We're going to talk about using some of the stuff with the graphing calculator, so let me pull up the graphing calculator. Oops. Let's pull up the graphing calculator. Come on, baby. Double click. There we go. That's what I wanted. Give it a sec to warm up, think about stuff. Ta-da. All right. And we can clear that. Close, close, close. Get rid of that. There we go. All right. So we're going to utilize that in a second. There. Let's go there. All right. Okay. So this particular function is basically like saying the same thing as 1 plus b raised to the x power. Okay, where our b value is the 1 plus r. If the b value is a value greater than 1, then you have growth. If the b value is a decimal or fraction, which is between 0 and 1, we have decay. Remember, growth, as I go to the right, as I go to infinity in the x direction, growth means it is growing away from my asymptote. If my b value, or my 1 plus r, becomes a value between 0 and 1, so a fraction or a decimal, so like 0.25 or 1/3 or something like that, that means as I go to the right, my graph approaches my asymptote. And that's kind of a big key right there. Let's see. Y is equal to the amount set after time. A is the initial amount. T is time in years. R represents the increased expressed as a decimal. And then 1 plus R is called the growth factor. Okay? Growth or decay. So 1 plus R is going to be growth because 1 plus a number is going to give me some value bigger than 1. If it was 1 minus R, it would be a decay. But that's where we're going to kind of base things on. Now, we're going to manipulate this equation a little tiny bit because there's certain things that happen. Now, I know some of you might have some sort of savings account. Maybe perhaps you're putting money in. Maybe a family has put money in for you. But that could take place. Or sometime in life, you're going to have that. So your money grows at an exponential rate when it's in the bank or in the stock market. There's a lot of different ways to kind of think about, how things would increase or decrease. Right now, coronavirus is on an exponential decay, which is great. Okay? Originally, when it first came out, it was on exponential growth. And when they kept saying there was a term they kept using like a year ago, and you probably remember this little story, let's all quarantine to home so we can, there was a term they used called flatten the curve. Flatten the curve did not mean that we got rid of and eradicated the disease. It just meant that it was no longer growing exponentially. It curved off at a sustainable rate. Now we are decreasing the number of infections for a number of reasons. One, we have a vaccine. Two, we have an awful lot of people who have had it. Yes, you can catch it twice. But the vast amount of people who have gotten coronavirus have only caught it once. They didn't catch it twice. So there's just a few things to kind of think about. I mean, we're living in a real-life exponential growth, exponential decay situation. Okay? Will coronavirus ever go away 100%? No. Okay? It's like measles. Will measles ever go away all the way? No. Do we have measles outbreaks that take place in the United States? Yes. Okay? Smallpox was almost completely eradicated from the planet. And how we eradicated it as a planet is the World Health Organization implemented worldwide vaccinations to smallpox. Okay, now, most of you have not gotten vaccinated to smallpox because there was something, I believe it was in 1982 or 1984, and I can't remember the exact year, and I apologize. But they stopped giving it. Now, I have on my left arm, I have a little tiny, if you look on my arm, there's a little tiny mark. Some people have a more pronounced mark that are like my age, and some have a real faint mark like mine. And I remember this was a vaccine that basically when I was 2 or 3 years old, got the vaccine. It almost completely eradicated smallpox from the human population. Unfortunately, in some countries where governments had fallen, the eradication process lessened and people came across it. There's other things like plague. Plague happens here in Colorado. It happens with our ground squirrels, our little gophers that we all see. Everyone thinks they're cute because they're all standing up looking around. They're like, oh, they're so cute, until you actually get one in your yard and they destroy everything. But we almost completely eradicated it, but smallpox does indeed still exist here on the planet. It has had small spikes in different places throughout the world. If it ever gets to an uncontrolled type of growth, they would have some sort of government action that would get everyone inoculated again to smallpox. Those who already had the smallpox vaccine might need a booster shot, but they might not. But it's just those are things that people that are really smart who study infectious diseases. It's not like one person who read something on a Facebook chat said, oh, I'm not a pro. I mean, the people who are making these decisions are really smart people. We want these types of people making decisions, okay? And we want really smart people making these decisions that don't make decisions based on politics or who's in power or what political party's in power. Politics and medicine should never go hand in hand with each other, in my opinion. Now, if you have a different view, I'm not trying to say your view isn't important. I'm just saying what I've seen is it gets nasty what society does. Unfortunately, we hear a lot of the naysayers, and unfortunately, we have a whole lot of people that have one of these fancy things that you all have, and I have, and I'm sorry, mine's smaller than the rest of yours, but mine fits my pocket. But people will research stuff to find what fits into their wheelhouse of ideas. There are 3 things I would strongly encourage you as smart people to never use the internet for. You should never use the internet for your financial advice. You should not use the internet to influence your political thoughts. And you should not use the internet to dictate your medical philosophies. I have one of my docs, she didn't speak this year with my med class, but her name's Dr. Jackie Mesa. And she is an infectious disease doctor. And she actually was sent overseas, was not able to make a video for me this year, but she has emailed me. She's back in the country, and she can't wait to come back and speak to our class. But she puts up, I think she talks about vaccines. And she puts up a picture of Jenny McCarthy. Jenny McCarthy is somebody who she posted in Playboy, and she's done other things, but unfortunately, her child was born with autism. She blames vaccines on her child's autism, is a big advocate. And Dr. Jackie Mesa brings up her picture and says, this is who this person is. She's a Playboy Playmate. I don't suggest you take medical advice from a Playboy Playmate because I don't either. And that's basically her dig on Jenny McCarthy. Okay. All right, so it says January 93, there was 1,313,000 internet hosts. And I don't know if this is real information or if this is just something that we made up, but they're just talking about this. It says during the next 5 years, the number of hosts increased by about 100% per year. So the internet has existed for a long time. It was actually a military operation. And then some of the universities, University of Minnesota really got on board with this. And they called their browser the Gopher, because University of Minnesota are the Golden Gophers, right? I don't know if you know that or not. But they were the ones that started utilizing the internet, and they basically put it out to their student bodies so they could research information without having to go to the library. Seemed like a good idea. Back then, the internet itself, you were able to search for things, and it had a web crawler, which basically went through and looked for certain keywords and phrases. And then it would bring up, these are the particular journals and articles. And there was no pictures, so it was not quite as fascinating as today. But at the time, it was really pretty incredible going, wow, I don't have to go to the card catalog, which was these big old stack of these things, and you open it up, and it's got all of these things, and you're like, okay, I'm looking for chickenpox. Okay, here's some stuff on chickenpox. Okay, this is an article in Scientific America, article January 1977. So then you could write down that information, because you couldn't take the card out. It was like fastened in there. You'd write down the information, and you'd go to the stacks in the library, which was basically a small warehouse of little tiny films called microfiche. What they did is they had taken pictures of all of these different journal articles, and you'd say, I need 1970, whatever I said, Scientific America, and they'd say, just a minute, and they'd walk back and they'd find in their microfiche, Scientific America, 1972, January 72, or whatever date I said. They'd bring it out, and they'd bring you a reel. It looked like a little tiny film reel. And you would take that and you'd put it in this machine, and you would feed it through the machine, and then it would feed through to the side, and you would search for the article that you were looking for. And that machine that you were on was actually a photocopy machine. So when you got to your page, you had to put a dime in, and it would take a picture and make a photocopy of the page you were looking at. I mean, this is what, honestly, this is my lifetime of how we had to do research. You know, now we have our best friend called Google, or whatever search engine you use, but I imagine most of you have used Google at least once. And some of you are like, I just do Ask Siri. Okay, that's great too. So it's really, the information highway has really taken off. The amount of research that you are able to do today is so much more vast than the research that was from the past, which is really pretty cool. Now, we've all seen things that are on the internet going, oh, that's silly, that can't be right. And you can't verify all the time if something is a legitimate thing or just a funny picture or a funny video clip. Okay? So, January 93, we were told there was this many, oops, go here, 1.31300. That was where I started. We're talking about 5 years. And number of hosts was increased by 100%. 100% as a decimal is 1.00. Agree? So now what we want to do is we want to figure out what happened in the next 5 years. Now, we're going to call 1993 is going to be 0. In 5 years, we're talking about 1998. That's going to be 5 years. You following my thought process so far? We're not worried about, 0 being the beginning of time. We're just worried about 0 being our very first time we were looking at something. So basically, this graph is going to look something like this, where this part of the thing is, we're not worried about that. But this line right here basically takes place at 1993. Okay? This over here is 92, 91, 90, all the way back to the start of time. So that's kind of what our graph's going to look like. So let's utilize our information. We're going to go back and take a look at this. We're going to say, we're going to use this equation, 1 plus a, 1 plus r raised to the t. So let's plug this in and figure this out. So our a value is this, 1 plus this, 1.00, raised to the 5, and that's the math that we're going to do. Now, do I really need 1.000 or 1.00? No. So this could clean up to look like this. And our calculator is going to handle something like this pretty easily. 1.313. So let's go here. We're going to go 1313. I forgot. 1.313. I got that right? 313000 times 2. And then I'm going to raise that to the 5th. So that means that in 5 years, the internet went from 1.3 million to 42,016,000 sites. It grew fast. Does our internet wealth of knowledge continue to grow every day? Yeah. I don't know exactly what the growth rate is. I don't know if it's slowed or if it's increased. But I think since you all probably first got a cell phone where you had some sort of access to the internet to today, you are seeing a lot more information. Now I realize Instagram and Snapchat and all the other things like that, there's a lot of information out there on it, right? That's not all the research that you'll ever do in your life, though a lot of that stuff is pretty entertaining. So that's basically how we do this kind of situation. Okay, the calculator, again, is a very valuable tool for you because, I mean, 2 to the 5th is 2, 4, 8, 16, 32. So you're going 32 times 1,313,000 to come up with 42,016,000. All right. Let's move on. Okay, so now we're going to take the same equation, but now we're going to change it to where we have this value n. And this means the number of times something's compounded. Okay, a lot of times money in financial things compounds certain amount of times through the year. If it compounds monthly, that means it compounds 12 times a year. If it compounds quarterly, that means it compounds 4 times a year. If it compounds yearly, it compounds once a year. If it compounds daily, it compounds 365 days a year. We ignore for the most part, we ignore the leap year, so we don't have to go 365.2416, which is what the leap year actually is. Okay, there's certain characteristics of the leap year that some years you would actually have certain times during different millenniums. So every 1,000 years, you might have a leap year 2 years in a row versus every 4 years. And they do that in order to catch up. It just means the rotation of the Earth doesn't truly take 365 days. It takes 365 and a little bit more. So we have to increase the leap year every 4 years for the most part in order to keep our calendar constant. Every now and then you might have 2 leap years 1 year after the next. But we've yet to really see anything like that. So the A, again, is the amount in the account after a certain amount of time. P is the initial principal, the initial amount that we put in. R is the annual rate expressed as a decimal. So if it was 75%, that would be 0.75. N would be how many times a year the interest is compounded. Okay, so we have 3 different items here. The 1,200 is going to stay. Whoops! Stop! Don't do anything silly, Stirrup. 1,200 is that. We're talking about 3 years, but then we have different percents. So we need to know that this is 0.025. Compounded quarterly means 4 times a year, so my n value is 4. This is 0.024. Compounded monthly, so my n is equal to 12. And this is 0.026 as a true decimal, compounded yearly, so n equals 1. And each of those is going to work using our equation that we saw, A equals P, 1 plus R over N raised to the N times T. And we can go ahead and do this problem. We can say, well, on this first problem, it's going to be 1,200, 1 plus R, 0.025 over 4 raised to the 4 times 3. And we could do that math. The second equation, I'll do it in a different color. So we can go A equals still the 1,200, 1 plus 0.024 compounded monthly over 12 raised to the 4 times 12. And then my last one, we're going to go A equals 1,200, 1 plus 0.026 over year over 1 raised to the 4 times 1. And each of those can be done on the calculator pretty quickly and easily as well. So I'm going to go 1,200, 1 plus 0.025 over 4 raised to the 12, 1,200, 1 plus 0.024 over 12 raised to the 4 times 12, which is 48. And then I have 1,200 raised to the 1 plus 0.026 over 1 time raised to the 4th. So I wrote those there so I could use those on my calculator. Okay, so let's plug those all into the calculator, see what's going to happen. Go back to the calculator. First one, I got 1,200. 1 plus 0.025 divided by 4 raised to the 12th. So there's my first answer. So if that was my bank account after the set amount of years, they said 4 years, I would have $1,293.16 rounded to the nearest penny. My second one, if I went 1,200 raised times 1 plus 0.024 divided by 12. And then this must be a huge number because it's raised to the 48th power. Well, yeah, it's a little bit more. So if it was compounded monthly, even though the percentage rate is a little bit lower, it got us a little bit more money. So $1,320.78 rounded to the nearest penny. And then the last one is 1,200, 1 plus 0.026 divided by 1. Technically, you don't really have to put that, but we'll put it just to keep it constant. Raised to the 4th. So this one actually showed us the highest amount of money, but it had a little bit higher percentage rate. It wasn't compounded as frequently, but because my percentage rate was a little bit higher, it gave us a little bit more money. So your percentage rate and your time are really the main things that are going to impact the information. And again, yes, there are some ways. Some people are like, oh, can I just combine those terms together and do it? You sure can, but you don't have to. Yeah. Where did the 4 come from? Oh, this one said it was compounded quarterly, so 4 times a year. And this one said it was compounded monthly, so there's 12 months in a year. That's where the 12 comes from. And, oh, wait. Should that have been a 3? Oh, boy, okay. Second, enter, make that a 3. Thank you. I made an error. Is that right now? Cool, thank you. Yeah. Oh, so notice. Oh, that was 3 times 12, so that should have been 36, shouldn't it? All right, let's see. We're going to go 1,200. 1 plus, all right, so 1 plus 0.24. Oh, wait. Stir up. Can't have fancy things. Divided by 12. And that should be raised to the what? 36? 36. Yeah, you know, if I did things correctly, it'd be nicer. I tell you. So that should have been to the 36. Sorry about that. So let's change that on here. So that should have been, it wasn't 4 times 12, it was 3 times 12. And that should have been 3 times 1. Sorry about that. I'm glad I'm amongst smart people. If I wasn't amongst smart people, I'd be teaching things wrong all day long. May I move on, my friends? All right. Oh, we got things to erase. Okay, so when a real life quantity decreases by a fixed percent each year, the amount of y of the quantity after t years can be modeled by this equation. Oh, there's the equation. Sorry that I didn't make it fancy enough that you could erase stuff. So notice the main difference in this is we're subtracting versus adding. Where r is the percent expressed as a decimal, and the quantity 1 plus r is called the decay factor. So it's decay if that middle, the in parentheses, becomes a value between 0 and 1. It's growth if it's bigger than 1. Can I move on? Do my butt? Where? Ooh. Okay, yeah. Anything else I forgot to erase? Anything there? No? Okay, new car is purchased for $24,000. The value of the car decreased by 16% per year, so that's 0.16. Write an expression for the decay for the value of the car. So 1 equals A, 1 minus R raised to the T. So I'm going to get y equals 24,000, 1 minus 0.16 raised to the T. If the car loses 16%, what percent does it, if the car loses 16%, what percent does it maintain? So if it loses 16%, I'm going to go 100% minus 16%. So that's going to give me, it means it's worth 84% originally what it was worth each year. So from last year to this year, it's worth only 84%. For next year, it's worth 84% it was this year. The following year is 84% the following year. Estimate the value of the car after 2 years. So I'm going to go 24,000, 1 minus 0.16 raised to the 2. You can plug that into the calculator, and that's going to give you a certain value. Okay? And I think you can do that. And then it says, estimate when the value of the car will be 12,000. So that means 12,000 is equal to 24,000, 1 minus 0.16 raised to the t. Ooh. So this, I'm going to have to come back and talk about a little bit more. Okay? There's 2 ways to do that. One of the ways I have not taught yet. The other way would be literally graphing each and every one. And I'm just looking where I'm at. Well, shoot, my friends. Will you do me a big favor? We're going to pick this back up next time where we're at. Will you do me a favor? Will you start on, and it's not due next time, but will you start on 9D? Start on means more than none, less than 100%. Is that okay? Because I want to make sure I cover this pretty well with you. And we're far ahead of everybody else, so I'd rather stay far ahead, but I also want to make sure we do it. Bring these notes back for next time. Get a start on that. Peace out, everyone. Have a great day. Take care of one another. Yeah.